So hello everyone, my name is Arash Babamiri and I'm a PhD student at Dublin City University in Ireland. Today I'm going to talk about part of my PhD project under the supervision of Dr. Aghamolaei. And today I'm going to talk about a BIM-Integrated adaptive surrogate framework for efficient uncertainty quantification in building energy simulation. So most of us have used machine learning to develop surrogate models, but only a few of us think about the very first step of developing these models, which is sampling. And the question is, have you ever thought about how many simulations actually your model needs to perform accurately, or you just simply increase the number of simulations, sometimes by hundreds or sometimes by thousands? So this is the type of question that I'm going to answer in this research. So I start with the outline of this presentation. First, I will talk about the background and research, then the methodology to answer that. A methodology to answer my research question, my results, and finally the conclusion. Before we talk about the surrogate model developing, let's take one step back and see why and where actually this process begins. So as we all know, buildings and construction account for 37% of global energy-related CO2 emission, and 75% of EU buildings are energy inefficient. And the annual retrofit in EU buildings is around 1%, which is very low, and it means that we need to integrate more up-to-date methodology. One of these methodologies is BIM, or Building Information Modeling, and we can use that for our base step to create our BIM model, or building energy model. But the problem is that the process is fragmented and the output is kind of deterministic, that masks the uncertainty of inputs. So we can answer the uncertainty by integrating the Monte Carlo simulation, but as we all know, the Monte Carlo simulation is also related, needs thousands of energy plus simulations. That makes it kind of hard and prohibitive to evaluate different metrics over different temporal resolution. So we can use meta model to quantify these uncertainties with lower computational cost, but most of the literature rely on static sampling, which I described the limitation before. So by far we understand that there is no unified framework and methodology to consider BIM sequential sampling and considering multiple output over different temporal resolution. So I formed my research question to tackle these limitations. So the research question is, how can an adaptive surrogate framework efficiently quantify uncertainty in BIM-based building energy models by combining sequential sampling? Here is the methodology to answer this research question. I developed 3 steps. In the first step, I collected the data and identified the most common Irish residential archetypes, and I used this for my case model only. These models are developed in Revit as my BIM tool, and then with the help of Pollination, I create my BIM model, and by manually adding information about occupancy, system, and weather and schedule, I create a simulation-ready BIM model in IDF format. Then I use these IDF files in the second step to create my surrogate models iteratively. To construct this surrogate model, I increase the uncertainty domain in 3 levels. In the first level, I only consider the envelope, solar heat gain coefficient, and infiltration. In the second step, I add operational on top of that. And in the third step, I integrated the WWR as a geometry variable. So by doing so, the iterative surrogate model started. So in each iteration, the quality of surrogate model is kind of evaluated based on some error metrics, and in each simulation point are added only where the surrogate model shows high uncertainty or poor local accuracy. Therefore, each additional simulation kind of create the maximum gain information. Then I use this surrogate model to quantify uncertainty and sensitivity analysis in the third step. So I benchmark my surrogate model with Monte Carlo simulation with 3 stopping criteria. And as you see in each step for different archetypes, it's kind of converged. And for the surrogate validation accuracy, I use R squared because it provides a quick measure on how well the surrogate model kind of produced the energy plus simulation. For EU, it reached 99%. For heat demand, it reached 93%, and only needs around 500 simulation per archetypes. By combining adaptive sampling and adaptive PCE, the framework achieved the accuracy comparable to Monte Carlo simulation, but with almost 8 times lower simulation. Then this model can be used for sensitivity analysis. The sensitivity analysis results show that the most influential feature are both archetype and performance metric specific, demonstrating that retrofit decision making should not be generalized across building types or performance output. So as a conclusion, Revit integrated with Polynomial and PyRevit can help us to create a simulation-ready BIM models. The sensitivity analysis shows that the results are archetype dependent and output dependent. And for future direction, we can broaden the archetypes to apartment or even commercial buildings. We can consider different and future climate scenario. For more efficient surrogate model, we can use multi-fidelity surrogate modeling, and we can integrated optimization under uncertainty. And thank you for your attention. And I have no more slides.
Thank you very much.